Hi, my name is Philip. I'm 17. Let me start with the background of the experiment I'm going to propose. We know from the general theory of relativity that clocks run slower, close to a massive body. Then they must run faster in a weaker gravitational field. Let's check it. We start with the moon. Hi Buzz, this is the Earth. Tell me, does your clock run faster?
Hi Philip! Oh no, it runs much slower.
Something wrong? Let's check in a place where the gravitational field is even weaker. Hello Dimitri, can you tell me if your clock is running faster than on the Earth?
No! Oh my gosh, it seems that it stopped!
So, we have something contradictory to the general theory of relativity. Okay, now it's time to be serious. I propose to investigate how some properties of granular matter are modified in a reduced gravity. In particular, the experiment question is how do the flow rate in an hourglass and the angle of repose depend on the gravitational acceleration g. A simple dimensional analysis says that the flow rate is proportional to the square root of g. The situation is less clear for the angle of repose. Experiments in parabolic flights suggest that the static angle of repose increases with reduced gravity, whereas the dynamic angle decreases. In the proposed experiment, we can verify this data. Since the effective g is 0 at the ISS, we have to generate a non-zero effective gravitational force in a controllable way. We propose to use a small centrifuge, like this. Here is a tiny hourglass, a counterweight, and a DC motor. Changing the applied voltage, we can control the angular velocity omega. The force acting on a given grain close to the orifice is equal to m omega squared r, where m is the mass of the grain and r is its distance from the axis. As a result, the grains would behave like in a gravitational field with g equal to omega squared r. Recording the flow or taking pictures at regular time periods, we can calculate how the float rate depends on the effective g. Similarly, we will be able to determine the g dependence of the angle of repose. We expect to confirm the square root of g rule or find corrections to this formula. It may be important in designing silos or hoppers for extraterrestrial bases. The knowledge of the g dependence of the angle of repose may be useful if we plan to mine natural resources on other planets, especially if you would like to store them in heaps.